I'll start kind of chairing.
Okay. Okay, so what I wanted to do today was to talk about some applications of random walks and particular spectral graph theory to the problem of characterizing graph structures. And what I'm going to do is to focus very much on problems from image analysis and computer vision. And I've put far too much into the talk, but what I want to do is really to pull out two topics in particular. One is how one can realize image smoothing as a diffusion process on a lattice graph. And the second thing is to show you how we can use some of the properties of random walks on graphs to arrive at high-level characteristics which can be used for problems involving the clustering of graphs representing image features. So this is work done in collaboration with a number of people. One of them is Richard Wilson, and the others are two research students of mine, Bei Zhao and Fan Zhang. So this is really the motivation for the talk. Those of you from the computer vision and image analysis area will know that there's been considerable amount of work on the development of graph spectral techniques for computer vision. And so possibly the most famous is Sheehan Malik's recursive bisection technique for image segmentation, which relies on the Fiedler vector to segment images. There have also been some other techniques which are perhaps less familiar. One of them is the work by Umiyama, who shows how graph spectral methods can be used to match graph structures with the same numbers of nodes but different edge structure. Shapiro and Brady have a similar idea aimed at extracting point correspondences for motion analysis problems, and Chacon, Fonde and Dickinson have used spectral methods for indexing trees representing image data. And what I want to do is to address some of these problems from a slightly different perspective, and that is to use random walks techniques to analyze graph structures that arise in image analysis and computer vision. And one of the important observations that comes out of this, and I'll describe some of the mathematics later on, is that the random walk on a graph is determined by the Laplacian spectrum for the Laplacian representing the graph. And in fact, one can determine a large number of properties of the random walk on a graph, not just its steady state, but also things such as commute time and hitting time from the Laplacian spectrum. And what I want to do is to use this kind of analysis to so that we can analyze and interpret spectral methods for the analysis of graphs. And the random walks approach is nice because it gives an intuitive understanding of some of the spectral properties in terms of properties of a graph, in terms of their path length distribution. So just to quickly review some of the related literature, what I've tried to do here is to touch on a number of areas. Lavache has prepared a very good summary and review of the properties of random walks on graphs and their links with the Laplacian spectrum. And then in both the pattern analysis, computer vision, and machine learning communities, there have been a number of attempts to use Laplace spectra and random walks to develop a wide battery of algorithms. And so, for instance, Gori and collaborators have formulated the problem of graph matching using random walks. Recently, Meili and Shi have used random walks to analyze the results obtained using spectral segmentation, and Gaharami et al. Have developed semi-supervised learning algorithms based on random walks on graph structures that represent labeling problems. So, also related to this is, of course, is all the work on using spectral methods to embed graphs in low-dimensional spaces. And so, for instance, Sarins et al. Have developed a technique for performing PCA on graph structures using the pseudo-inverse of the Laplacian matrix. Borgwart has developed random walk kernels on graphs which are determined by the Laplace spectrum. Lafon and Koifman have recently developed the diffusion map, which is an embedding of a graph into a vector space that preserves properties of the random walk. And with Huijun Cui, I've recently developed a method for image segmentation and multi-body motion segmentation that relies on the commute time embedding of nodes of a graph into a pattern space. And this embedding is such that the distance between nodes under the embedding preserves the commute time of the original graph. If one's looking at this from a sort of practical perspective, then random walk algorithms have been developed, and I'll show you some of them in this talk, for a whole number of different applications involving image data. So, for instance, image smoothing can be realized as a process of smoothing an image with a heat kernel, which describes the random walk on the graph. Graph simplification can be realized using random walks and spectral methods. So by graph simplification, what I mean is converting a graph into an equivalent tree or string representation. As I said on the previous slide, embeddings can be used to embed graphs in low-dimensional vector spaces. And what I'll show later on is that it's also possible, using the Laplace spectrum, to extract permutation invariants from graphs, which can be used to characterize them for the purposes of clustering and high-level analysis. So these are some of the practical algorithms that come out of the random walks analysis of graphs and the link with the Laplace spectrum. So this is the outline of the talk. What I want to do is to begin by giving you some spectral graph theory and explaining the links with a random walk on a graph. And then what I'll do is give some applications of continuous and discrete time random walks. What I want to do is really just to focus on two of these, although I'll skip over a number of others. And then at the end, if I have time, to talk about how quantum walks, which are a development out of quantum computing, can be used to overcome some of the problems with classical random walks, in particular the problems of co-spectrality. And then I'll provide some conclusions. So what I want to do in this next 5 minutes is really to explain the relationship between graph spectra and random walks, and explain how the spectrum of the Laplacian matrix can be used to compute quantities such as commute time and hitting time for random walks on graphs. So this is really the mathematical setup. We start with an adjacency matrix, or a weighted adjacency matrix. For each node in the graph, we compute the degree, which is the sum of the edges or the sum of the weights incident on a particular node. And then the Laplacian matrix is just the degree matrix minus the weight matrix. And the idea is to, in spectral graph theory, is to take the Laplacian matrix and decompose it into eigenvectors and eigenvalues. So here is the spectral decomposition of the Laplacian matrix. Phi is the matrix with the eigenvectors as columns. Lambda is a diagonal matrix with the ordered eigenvalues on the diagonal. And so these are the ingredients. Here are the ordered eigenvalues. For the Laplacian matrix, the smallest eigenvalue is 0, and its multiplicity tells you the number of connected components in the graph. So here's a quick summary of the properties of the eigenvalues and eigenvectors of the Laplacian matrix. The eigenvalues are positive and the smallest eigenvalue is 0. The multiplicity of the 0 eigenvalue is the number of connected components in the graph. The 0 eigenvalue is associated with an all ones vector, and the eigenvector associated with the second smallest eigenvalue is the Fiedler vector. and it's the Fiedler vector which has been exploited all over pattern analysis and computer vision to develop algorithms, particularly the Sheehan-Malik segmentation algorithm. So what I'm going to be interested in here are random walks on graphs. There are two types of random walk that one can easily analyze. The first of these is a discrete time random walk where the state vector is time t is just found by multiplying the state vector at time t minus 1 by a transition probability matrix. This transition matrix is just the inverse of a degree matrix times the adjacency matrix. And the steady state of the discrete time random walk just satisfies the following equation: P of s equals t times P of s, and this is determined by the leading eigenvector of the adjacency matrix, or equivalently the Fiedler vector of the Laplacian. What I'm going to focus on rather more in this talk are the properties of continuous time random walks on graphs. And for a continuous time random walk on the graph, what we're interested in is the solution of the heat equation. I've written the heat equation here. It's dH dt equals minus L times h of t, where ht is the heat kernel. And if we recall the expression for the Laplacian matrix and its eigendecomposition, then since the solution of this equation is just an exponential of the Laplacian with time, we can solve this equation using the spectrum of the Laplacian matrix, and the heat kernel is just the eigenvector matrix times the exponential of the eigenvalue matrix with time times the transpose of the eigenvector matrix. So that's the heat kernel. Why is it interesting? Well, if we write down the differential equation for the state vector of a continuous time random walk on a graph, it's dp dt equals minus L times p, where p is a vector which has the probabilities of visiting nodes at time t as its components. And if we solve this differential equation in a similar way to the way in which we solved the one on the previous slide, then the state vector at times t is just the e to the minus lt times the state vector at times 0, and we know that e to the minus lt is just the heat kernel. So what happens is the heat kernel controls the evolution of the state vector of the random walk with time, and since the heat kernel can be written in terms of the spectrum of the Laplacian matrix, then it's the spectrum of the Laplacian matrix that determines the properties of the continuous time random walk. Now, there are a number of interesting properties related to the heat kernel. I just want to skip over some of them here, but I'll come back to them in the latter part of the talk when I come to talk about characterizing graphs. One of them is that the heat kernel of the graph can be expanded in terms of the number of paths, weighted paths of length k between a pair of nodes u and v. And so the heat kernel of the graph is in fact determined by the path length distribution. And so if we want to think about what the heat kernel means, it's really an encapsulation of the distribution of paths over a graph, and we can probe this path length structure using a Laplacian spectrum. So for instance, this pkuv can be determined in terms of the eigenvalues of the Laplacian matrix and its eigenvectors. Now, something I want to come on to at the end of the talk is to exploit this relationship between path lengths and the spectrum of the graph. And one way of characterizing a graph is to use something called the Ihara zeta function. And the Ihara zeta function is just 1 over the characteristic polynomial for the graph. So the characteristic polynomial is the determinant of the identity matrix minus s, where s is the variable of the zeta function times the transition matrix. And this can be expanded in terms of prime paths, and you can think of the prime paths as being rather like prime numbers, but on a graph. the Ihara zeta function can be expanded in terms of prime paths in the following manner, where C of P is the length of a particular prime path on the graph. And if we take the logarithm of the zeta function, it turns out to be a polynomial series in the argument S, and it turns out that the coefficients of that polynomial series are the number of paths of length k on the graph. So this really sort of explores the relationship between a characteristic of the graph, the Ihara zeta function, and the distribution of path lengths. As I said, I want to come back to this at the end of the talk when I describe means of characterizing the properties of graphs using simple characteristics, and I'll show how those are related to properties of the path length distribution on the graph, a particular number of spanning trees contained within a graph. Okay, so what I'd like to do is really to spend some time talking about the first of the applications that I wanted to explore in this talk, and that is to use the use of path-based methods. And here the Fiedler vector has been used in a number of applications to sort the nodes of a graph into a serial or string order. So this property has been used in a number of domains, not just in computer vision. It's exploited widely in routing problems and also in the development of search algorithms. So let me give a little bit of a motivation as to why the Fiedler vector is an interesting thing to look at. So here is what I've done in this slide here is to take a graph, and then what I've done is I've computed the spectrum of that graph, and from the graph I have computed the heat kernel. So the heat kernel, if you remember, is found by exponentiating the Laplacian eigensystem with time. So, and then what I've done is I have computed the minimum spanning tree for the heat kernel. So in this, what I've done is I've taken this graph, I've computed its heat kernel, and I've associated with each edge a weight that is the corresponding element of the heat kernel for a pair of nodes. And then what I've done is I've computed the minimum spanning tree of that weighted graph, where the weights of the graph are in fact the elements of the heat kernel. And what you notice is that as I increase time in the computation of the heat kernel, then an interesting thing happens to the spanning tree. The spanning tree commences by being rooted at the center of the graph and being bushy in structure. And then as I increase the time in the heat kernel, then the spanning tree evolves into a structure which is very string-like. And that when I take a very large value of t, what happens is that the minimum spanning tree tends to be a sort of string winding itself around as many of the nodes in the graph as possible. And then there are a few branches that come off that string which connect to the more inaccessible nodes in the graph. So, in fact, this when I take t to be large, then the heat kernel is dominated by the Fiedler vector, that is to say the second smallest eigenvalue, and so it's this string-like behavior which is determined by the Fiedler vector of the Laplacian. And in fact, what algorithms based upon the Fiedler vector are doing is attempting to unearth this string ordering of the nodes, which I've shown here. So, I mean, just to quickly skip over one application of the Fiedler vector in pattern analysis problems. One of the things we can try to do is to find a permutation pi that puts the nodes of a graph into a string order that effectively minimizes the sum of weights as we go through the graph. And what Henriksen and co-workers have shown how that problem can be relaxed into an optimization problem involving a continuous indicator variable that represents the permutation, and they've shown that the solution to this minimization problem is in fact determined by a Rayleigh quotient, and the solution is given by the Fiedler vector, or the eigenvector associated with the second smallest eigenvalue of the graph. So what I've done here is I've shown how this property can be used to sort the nodes of a graph into a serial ordering. And let me just show you an example here from a computer vision problem. So this problem arises in something known as surface integration, and this is a subcomponent of the shape from shading problem. What shape from shading gives you is a field of surface normals at each location in an image, and these surface normals are recovered by trying to solve the image irradiance equation. And from the field of surface normals, what we wish to do is to recover the height function of the associated object. So the way in which the height function can be recovered is to find an integration path through the field of surface normals, to traverse that path, incrementing the height function using the tangent of the angles between the pair of surface normals visited, and from this we can recover the height. And so what I've done here is I've used the Fiedler vector to find a path through the field of surface normals such that I minimize the difference in surface normal direction between each successive path. And this is coded up as these differences in surface normals are coded up as a weighted graph. And what I've shown here is the integration path that minimizes the difference in surface normal direction, and then here a number of views of the reconstructed surface that arises. So that's an example of using the Fiedler vector for a path-based problem in computer vision. What I'd like to spend some more time doing is talking about the relationship between the heat equation and the diffusion smoothing of images. So this is a problem that has been studied for a long time in the image analysis literature, and probably the most famous algorithm that exists for it is the Perron-Malik anisotropic diffusion algorithm. What I want to do is to show you how diffusion smoothing of images, I'll not just consider grayscale images, but I'll also consider more complicated data types, for instance diffusion MRI data. I'll show how this process can be formulated on a graph and the solution delivered by the Laplacian spectrum. So let's begin this discussion. What I've written down here is the general diffusion equation as a partial differential equation. So what we have here is U as a representation of the image, T is time, and what this says is that the du dt is a divergence of d dotted into the gradient of the image. And for instance, if we take d equals 1 in this process, then what happens is we recover isotropic linear diffusion, and it's well known that this can be realized using Gaussian filters. If we have d as a scalar function, then we have inhomogeneous diffusion of the Perron-Malik type, where the du dt depends on a function of the image gradient, and then the recent work by Weikert et al. Takes a more complicated form of d and in fact uses a 2x2 diffusion tensor instead. So the observation here is that this differential equation can be thought of as a heat equation on the graph, and what I want to do is to show you how we can give it a graph setting and then find the solution using the Laplacian spectrum. So this is really some of the motivation for doing it in the graph setting. Most PDE approaches assume that an image is a continuous function and then consider the discretization of this function for numerical implementation. And this is really where all the problems come in, trying to convert a continuous PDE from the space of reals onto a pixel lattice. And the number of weaknesses that arise from this. First of all, noisy images may not be sufficiently small to give reliable discrete estimates of the derivatives required to perform this process, and as a result, fast and stable implementation can be difficult. So what I want to do is to show how we can set the problem up instead, right from the outset as a discrete problem, using a diffusion on a graph. And what we're going to do is to use the heat kernel as a smoothing kernel in order to try to obtain smoothed images with time as a variable. So this is how this proceeds. We set up the diffusion process as a problem involving a weighted graph, and the anisotropic smoothing is modeled by an edge weight matrix. And the idea of this edge weight matrix is that it's going to, we're going to have large weights associated with strong discontinuities in the image, that is to say edges, and we're going to have low weights when we're in regions of smoothness. And when we set the problem up in this way, the heat equation will allow easy flow of information along the low edge weights, and it will impede the flow of information across the high edge weights. Diffusion in this setup is going to be heat flow on the associated graph structures. Obviously the nodes here are going to be pixels, and the diffusion of grayscale information is going to be along edges with time. And what I want to do is, as I said before, is show you how the solution of this is given by the spectrum of the associated Laplacian matrix. So this is just really a picture illustrating the setup, an image represented as a lattice with the nodes as edges, as pixels, and the connectivity information on the pixel lattice represented as weighted edges. So what we're going to do in order to set this problem up is to take a pair of pixels and define a similarity weight between those pixels. A number of ways of doing this. A simple way is simply to take the difference in grayscale values at the pixel locations. More complicated thing, and this is what we've done in this work, is really to take neighborhoods around each pixel and then to compare the distribution of pixels within the neighborhood. And then once we have the distance function defined between a pair of pixels, we compute our weights by exponentiating the difference in neighborhood pixel values. And so if a neighborhood is similar, we get a weight which is close to 1. If we have a dissimilar neighborhood, we get a weight that's close to 0. So the idea, as I said before, is to use the random walk idea that I introduced earlier to develop a diffusion smoothing process on this graph, this pixel lattice representing the image. And then what I'll show is that we can use the heat kernel associated with that random walk as the smoothing kernel for the pixel grayscale values. So this is how the problem gets set up. What we do is we encode the pixel grayscale values in the image as a long vector, and then evolve the components of that long vector using the heat equation here. So di dt is minus L, the Laplacian matrix, times I. And so the pixel values here are stored as a long vector, and the connectivity structure and weight structure of the pixel lattice is encoded using a Laplacian matrix. So this is the solution that we get, that the pixel grayscale values at time t are just given by e to the minus t times L times their initial values, or the heat kernel times the initial values. And if we write this out as a component-wise convolution, this is what we get. The smooth pixel values are given by the initial values convolved with the heat kernel. So that's the general setup. And of course, it's interesting to see what happens here for small t behavior, because that means we can have an insight into what the exponential operator is doing. So if I expand the above equation for small t, then I get that I of t is I of naught into the identity matrix, minus d minus w, that's the Laplacian, times time. And I can now separate this out into two components, one of which is the initial grayscale value, and that's multiplied by 1 minus t. And then I have t multiplying the convolution of the surrounding pixel values with the weight matrix. So the weight matrix here is forming a filter that sort of smooths the image, and that's we multiply that by time and add it to 1 minus time times initial value, and so the initial values persist with decreasing effect as time increases, and as time increases, then the weighted smoothing of the image begins to dominate. So I think I've sort of explained that at least verbally on the previous slide. Of course, one of the problems with this is if we're going to implement this spectrally, it's going to involve computing the Laplacian spectrum of a very, very large matrix. I don't want to dwell on how we got around this, but the solution comes from using the Kirchhoff technique, and that gives us a more efficient algorithm. Okay, so let's have a look at some results. What I've done is I've taken an image, added some noise, and then applied the smoothing to the resulting image data. And so what we have are the image, the smooth results, and then adding noise and the smooth results. So, I mean, in terms of smoothing performance, it's probably meaningless to talk about this unless we try to compare it with some competing algorithms. So that's what I've done in this slide here. I've taken images, I've computed the initial RMS error, and then what I've computed is the RMS error after I've applied, first of all, the graph smoothing technique, secondly, the Perona and Malik algorithm, a number of other techniques, but importantly, a wavelet smoothing technique. And what you notice is that the graph smoothing technique competes very favorably with both the wavelet and the Perona-Malik algorithms in terms of reducing the RMS error. So we can look at that as a more systematically. So here what I've done is I've plotted the RMS error as a function of added standard deviation of added Gaussian noise, and what we've done is we have plotted the performance of a number of algorithms in this plot here. So the black curve is the initial RMS error, and then the graph smoothing is this red curve down the bottom. What you'll notice is it sort of dodges in and out of the points that I get from the wavelet technique, and the Perona and Malik algorithm sits slightly higher here. So realized in this way, we get an algorithm that certainly competes with wavelets and Perona-Malik in terms of its performance. And I mean, this can be applied to color imagery. And what I wanted to do is just to spend a little bit of time talking about a much more demanding application of the method, and this is to fiber track smoothing in tensor MRI data. In tensor MRI, diffusion tensor MRI, what we have is a tensor that characterizes the direction of water flow at a location in a volume, and what we want to do is to try to smooth such images so as to encourage fiber tracts, that is to say pathways from one image location to another. And what we do in order to get this characterization, I won't go into the details, is that we compute the eigenvectors of the diffusion tensors and compute the angles between the eigenvectors and use this to determine a weight that encourages diffusion along the fiber tracts but discourages diffusion perpendicular to them. So this is, as I say, this is actually quite a difficult problem involving a number of technical hurdles because diffusion tensors are non-Euclidean and they reside on half cones, and so in order to get the statistics right here, we have to go and use some techniques from the analysis of non-Euclidean statistics. So here are some examples. These are three different synthetic tensor fields representing a number of different sort of configurations. Here I have two sort of regions. Here I have a circular structure, and here I have a sort of wiggle going across a volume representing a potential tract. Then what I've done is I've added noise to that data and then applied a number of different techniques to smoothing it. So this is the graph-based diffusion technique, which nicely aligns the different tensors. Then I have the next slide. What I've done is I've plotted the results obtained by using Penetch's Riemannian smoothing technique to the tensors, and these are a little bit noisier. And then what we have here is an analysis again of root mean squared errors for the synthetic data. So here is the initial, the black curve is the initial RMS error, the red curve is the graph smoothing technique, and then the blue curve are the results that we get with Penetch's Riemannian smoothing. And the observation here is that we seem to do well in terms of reducing the RMS error. Okay, so let's have a look at some examples on real-world data. So this is these are tensor fields from real-world MRI data, and then what I've done is I have taken some sections of these and showed the effects of applying the graph smoothing technique to them. And so this is the initial image, and here's the result of applying our graph-based diffusion technique to the imagery. And again here. And so the effects here are to generally speaking, improve the connectivity, the flow structure in the tensor field, whilst not blurring image detail. And then finally, what we've done is we have tried to use these the smoothed images for fiber tract tracking. And so here what we've done is we've applied a particle filter to the unsmoothed and smooth particle tracts, and these are the results that we get. I don't want to dwell on this too long. Here is applying a particle filter to track the fiber tracts in the imagery without smoothing, and then here are the results that we get if we apply our graph-based smoothing technique. And so the general conclusion here is that we tend to concentrate the tracts followed by the particle filtering algorithm into a much better defined region in the image. Okay, so I think that's really all I want to say about the smoothing problem. Just a quick advertisement to say that this technique can also be applied to the problem of consistent labeling. The observation here is that the heat equation, when regarded as a probability update equation, looks very much like the sort of iterative processes that are applied for relaxation labeling. And what we've done is we have seen whether we could develop a spectral version of relaxation labeling based on a representation where we have a graph where the nodes represent possible object label assignments, and the weighted edges between the nodes represent label consistency relationships. And this has allowed us to address quite successfully a number of data labeling problems, including these ones here, which involved heavily overlapped clusters. So I don't really want to dwell on that. What I do want to do is to go ahead and talk about the second problem very much at the other end of image analysis, and see how we can use the heat kernel and invariance extracted from it as a way of characterizing graphs in a permutation invariant way. So let me just motivate this this problem a little bit, try to set the scene. So what I'm concerned with here is the problem of performing pattern analysis with graphs and trees. So normally in pattern analysis, what you're given is a vector representing data, possibly in high dimensions, and one then sets about the analysis of that vectorial data. And there are a whole number of well-established techniques for processing data in graph form, and pretty well most of current machine learning theory is based around such representations. However, if I'm given data in the form of a graph, then I have a problem, because whereas when I'm given data in the form of a vector, I know what the ordering of the data elements is. In the case of a graph, there is no canonical ordering. So what that means is that in order to analyze graph data, somehow I either have to establish correspondences between the nodes of the graph, or I have to find some way of summarizing the graph in a manner which will not be affected by the reordering of the nodes of a graph under a permutation. And it's this problem that I want to focus on in this last part of the talk. So here's an example. This is again taken from a computer vision problem. What we have here is a sequence of images of a model house, and what's happening is that the camera is panning around the object, and the viewpoint is changing slightly with each frame. And so what happens here is that as the camera pans, then some of the features come into view and go out of view because they become obscured by the foreground. And additionally, the relative distances between the features and the image change because of perspectivity. So what we've done in this example here is to extract feature points at image locations which correspond to the whereabouts of sharp corners. And then what we've done is we've taken those corner points and we've tried to extract a graph representation from them. So the graph representation is very simple. In fact, it's the Delaunay triangulation of the feature points, that is to say the points of high curvature in the image. And so to construct the Delaunay graph, what you do is you take each feature point, you seed a circle at that point, which grows in radius, and then that seed continues to grow until it collides with the region seeded at an adjacent point. The collision front between two growing circles is going to be a straight line, and this tessellation divides the image into a number of polygonal regions. And so what we've done is we've constructed the Delaunay graph, which is the region adjacency graph of the polygonal regions. And this is the resulting graph structure underneath, where the images correspond to the graphs correspond to the images. And what you see is that, generally speaking, the structure of the scene remains the same. But if you look in detail, what happens is that certain edges come into being and then vanish again, and also some of the points, the feature points, appear and then disappear. And so what we're dealing with here are graphs where we have, first of all, the edge structure changing with view number, but also the nodes constituting the graphs also come into existence and then go away again. So if we want to try to characterize this problem so that we can attempt to do some learning of the variations in those images and the associated graphs, there are a number of problems. The first problem, as I said, is that graphs are not vectors. We have no way to associate in a canonical manner the nodes in graphs corresponding to different views. And then what we need to do is to try to characterize the structural variations that take place, the variations in edge structure and node structure. And since the number of nodes are not fixed and we're not dealing with vectorial data, then there is obviously a problem in dealing with this problem, in this process. So what I want to do in the latter part of the talk is to describe a way which we can try to summarize the properties of graphs in a manner that doesn't involve computing correspondences and which is invariant under permutation of the node order of the nodes in the graphs. So this just really summarizes what I said there. If we want to overcome the problems of graphs being non-vectorial, we can try to establish correspondences between nodes. This is in many ways a brute force a solution to the problem that requires a lot of computation time. The alternative is to try to extract characteristics from graphs which are invariant to permutation of the node order, and in particular we can attempt to do this using graph spectral methods, and I'll give you a little bit of an insight into how the heat kernel provides us a convenient representation which we can use for this purpose. Okay, so let's take an example. What I've plotted here are 4 different graphs, and you can see that what is happening is the sort of complexity of the graphs is changing as I move from left to right. And so the first graph is just a square, the second graph is a pentagon, then I have a dumbbell structure here, which is effectively it's 2 pentagons connected by an edge to a root node, and then what I've done is I've increased the complexity of the dumbbell by connecting up the nodes which form the base of the dumbbell. And then what I've done here is I've plotted the trace of the heat kernel as a function of time. So the trace of the heat kernel is just the sum of the eigenvalues of the Laplacian matrix exponentiated with time, and if we do that and look at the form of the heat kernel trace as a function of time, you notice that we get a rather different form of the function for each of the graphs. And so, for instance, these 2 graphs here produce the 2 curves down at the bottom. The 2 graphs here produce the light blue and the dark blue curves. What you'll notice is that the light blue and dark blue curves are actually quite similar to each other, and then as we increase time, then the differences between them become obvious. So what's happening here? Well, the dumbbell graph and its sort of filled in version are in fact graphs which are tending to be bipartite. If I deleted this node in the middle, they'd form 2 different components. And for such graphs, the second eigenvalue has a relatively large value. What that means is that that determines the form of this curve here. In the case of these 2 graphs, that's not the case, and I get a very different behavior of the function near the origin. So what I'd like to do is to find a way of characterizing the properties of the heat kernel trace. So what I'm going to do is I'm going to return to the zeta function, not the Ihara version that I talked to you about in the first part of the talk, but Rosenberg's version, which depends on the eigenvalues of the Laplacian. And according to Rosenberg, the zeta function is just the sum of the non-zero eigenvalues that discards the 0 eigenvalues, the eigenvalue to minus the s. So what does this function mean? Well, the analysis which tells you what it means is given on this slide here. If I take the one of the terms that appear in the definition of the zeta function, lambda to the minus s, then I can rewrite it using the following Mellin transform. So it's just 1 over gamma s, t to the s minus 1, e to the minus lambda dt, integrated over t between 0 and infinity. And here gamma of s is just the standard gamma function. Now, what does the trace of the heat kernel mean? Well, it's just the number of connected components in the graph, the number of times I get a 0 eigenvalue, plus the sum of the non-zero eigenvalues, e to the minus lambda it. So now if I then sum this expression here over all possible lambdas, then the relationship between the zeta function and the heat kernel trace becomes clear. The zeta function is just the sum over all for all non-zero eigenvalues, lambda to the minus s. That's just going to be 1 over gamma s, and it's going to be the Mellin transform of the trace of the heat kernel minus the number of connected components. So what this means is that we can think of the zeta function as being the normalized moment generating function of the heat kernel trace. So this is what happens if I plot the zeta of s for each of the graphs that I showed you in the previous slide. And so what we now get are different curves representing the different graphs. The thing to note here now is there's a bigger separation between the dark blue and the light blue curves corresponding to the two variants of the dumbbell graph, and we also get more separation between the pentagon and the square graph at the bottom. So the idea is to use the zeta function as a characterization of graph structure. What I'm going to do is just sample it at various integer values. So here's some experiments on doing that. What I've done is I've taken the COIL database. Just to remind you, what happens in the COIL database is we have a number of different objects. For each object we have 72 different views corresponding to different viewing angles of the object as we pan around the circumference of the object with the camera. And then what I'm going to do is extract graphs from those views and then compute the zeta functions of the graphs and see whether I can use those as a feature vector to characterize the different objects. So these are the results that I get. Here are the zeta function evaluated at different values of s. So I've chosen 1, 2, 3, 4 here. So this is 1, this is 2, this is 3, this is 4. And then what I have are 4 different curves in each plot. The x-axis corresponds to the 72 different views of the different objects, and then the different horizontal lines correspond to the value of the zeta function for argument 1, 2, 3, and 4 for those 72 different views. And what you notice is that the zeta functions for the different graphs are pretty well separated if I take just a single value of s. And in fact, if I now make a feature vector of the 4 different values, then they're even better separated. And so if I now do PCA, principal components analysis, on a feature vector where each graph is represented by a vector of the 4 components, the 4 different values of the zeta function, these different colored clusters correspond to the different objects. And so they separate very nicely under PCA. And this is what happens if I simply use the Laplacian spectrum for the 4 different objects. You'll notice that the clusters are much more overlapped. So it seems like the zeta function is doing something very useful to the Laplacian spectrum in terms of separating the objects. So we're certainly winning when we use it. Okay, so this is just experiments on a more extensive data set. It's in fact the core database with 9 objects rather than 4, and we get a similar nice separation between the different objects. The different color here corresponds to a different object. And we've also applied this to the Oxford Caltech database using a representation, I won't go into its details, based on line segments rather than points. And again, we get a nice separation of objects. Okay, so there's one more thing I'd like to do just to finish the talk off, and that is to go back to the zeta function and have a look at one specific property that it has, and that's the value of its derivative at the origin. So So this is, just to remind you, this is the zeta function. It's defined as a sum over the non-zero eigenvalues, lambda to the minus s. I can rewrite that in terms of the following natural exponential, and so that makes differentiation easy. If I differentiate this, what happens is I pull down the logarithm of the eigenvalue, and then if I then re-express this and evaluate the derivative at the origin, it turns out the derivative of the origin is just minus the sum of the logarithm of the non-zero Laplacian eigenvalues, or the logarithm of 1 over the product of the non-zero Laplacian eigenvalues. So, why is that interesting? Well, there's a paper by Mackay from about 10-15 years ago where he shows the relationship between the shows the relationship between the Laplacian spectrum and the number of spanning trees in the graph. And what he shows is that the number of spanning trees is the product of the degrees of the node divided by the sums of the degrees of the nodes times e to the minus the derivative of the zeta function at the origin. And so really, by taking the product of non-zero Laplacian eigenvalues here, what we're doing is taking a measure that is related to the number of spanning trees in the graph. So let's just see how this works as a feature. Here's here's computing that unary feature, that the derivative of the zeta function at the origin for different objects in the coil database. Here operating with 8 different objects, and what you see is that we have view number along here. The different objects are all very well separated by that measure, and it seems to be a good choice of unary feature if we want to characterize the graphs. This is doing the same thing for the Oxford Caltech database. Here is a plot which I don't want to unpack too much because describing what's going on is quite complicated. But in principle, what I can do is I can think of the product of a non-zero eigenvalues as one polynomial that can be constructed over the Laplacian eigenvalues. The simplest polynomial that I can compute is obviously the sum of the eigenvalues, or the trace. And what I've done here is I've shown you other symmetric choices of polynomials in between the trace and the determinant. So what we have here is the for the objects in the Caltech database, what I have is the polynomials, the mean value plotted, and then the error bars show the variance of that polynomial for the class of objects. And what you see here is that if we look at where we get best separation between the objects based on different polynomials of the Laplace spectrum, we get the greatest separation if we take the determinant, and somewhere in the middle we get the worst separation. So it seems that the determinant here, the product of a non-zero eigenvalues, is possibly the best choice as a spectral feature for separating graphs. And here's a similar plot for the Oxford Caltech database, and exactly the same conclusion. So I think that's really all I want to say. I'll just skip briefly through the last section without going into any detail, but obviously one of the problems that can confound this spectral analysis of graphs is that if we take two graphs that have different structure and they give rise to the same spectrum, that problem is known as co-spectrality, and it is particularly bad for trees. In fact, it's known that almost all trees are co-spectral. What we've been doing recently are looking at different types of walk, particularly things called quantum walks, which have a rather different structure, and seeing whether the spectra associated with these walks can resolve some of the problems of co-spectrality that hinder classical methods. I don't really want to go into the details, but all I want to do is to show you this plot here, where we have taken all trees in up to 24 nodes, and what we've done is we have computed how many are co-spectral if we just use the Laplacian matrix, and how many are co-spectral if we use our characterization based on quantum walks rather than classical walks. And so the spectrum here is based on a rather different matrix operator, and what we see is that that choice of matrix operator reduces, in the case of 24 trees, which is as far as we could go, given the sort of the computing power available, we reduce the number of co-spectral trees by a factor of greater than 10. And so this representation would appear to be a powerful one for analysing the spectra of graphs. Okay? So just to conclude, random walks provide a powerful framework for path-based and flow-based analysis in vision and pattern recognition. They're convenient since they rely on the Laplacian spectrum, and although the eigendecomposition can be time-consuming to compute, the implementation of these algorithms is very, very straightforward. And what I hoped you could get a flavour of from this talk is that both low-level and high-level vision problems are amenable to this sort of analysis, because I showed you how we can both smooth images and also do problems such as object recognition based on the same basic representation. So thank you very much indeed.
Can you say something about the robustness of the methods for example, object recognition on the cloud database, and whether it's you can deal with clutter in the background?
We have done some experiments. Once the node number starts to be very different, then you start to run into problems. But if I go back to the slides here, the coil database, for the objects we were dealing with, we were probably getting something like 10% variance in node number across the views. And so what you see is that the error bars, the jitter here really is the error bar in the quantity. The error bars associated with those node variations is not having a significant effect in terms of overlapping the different curves. So I think, I can't remember the exact statistics, I think we were dealing with about 150 nodes with the coil graphs, and they were the number of nodes in a graph representing a particular object was varying perhaps by 10 or 20 over the image sequence. So I think that demonstrates the robustness to something like 10% node variation. Okay, so I guess it's lunchtime.